So we're going to start today just talking about momentum and what's called impulse. Okay, momentum and impulse. And then we're going to move into collisions. We're going to do a pretty cool lab with this chapter on an air track where we get to see collisions happen kind of in real life. And then we will work our way into two-dimensional collisions. But we're going to start with momentum, okay? We talk about momentum using the frame of reference with inertia. Anybody remember what inertia is? Newton's No. I like the definition, but that's energy. Okay. Anybody else? Inertia? Newton's first law. Yeah, right. It's Newton's first law. And it says objects in
motion stay in motion.
Yeah, sorry. Is that what it said, Hamilton?
Stay at rest.
There you go. Objects in motion stay in motion. Objects at rest stay at rest. Okay, so that means that inertia is an object's resistance to change, right? A resistance to change. It doesn't want to change. So when we look at this, we're going to start looking at how momentum helps us understand collisions and what that means, right? When I say collisions, what do you think of? Right? Just literally when anything collides. Happens all the time. So we're going to look at two different types of collisions, okay? The first type of collision we will look at is called an elastic collision. And an elastic collision is when objects rebound off of one another or bounce off. Okay, when we say rebound off of each other, that means they hit and then they bounce apart. Can you think of a real life example of an elastic collision?
Like a ball hitting a wall.
That's right, a ball that hits a wall. What else? Most types of sports are elastic collisions, right? Anytime you bounce a ball, anytime you hit an object, like playing pool is a textbook example of elastic collisions, right? You hit the cue ball hits another ball, right? It makes it move. That's a perfect example. And in perfectly elastic collisions, kinetic energy is conserved. So since we just finished kinetic energy, I want you to kind of break down this statement for me. If the kinetic energy is conserved in this collision, what does that mean?
It transfers from one to another.
Bingo. It transfers perfectly from one to another. And so this is where we get a good example of this, and in pool specifically, right? If I have a ball at rest, I hit the cue ball, right? If I have a perfectly elastic collision and the cue ball contacts this ball, what should happen to the cue ball? It should stop, right? And all of the energy from the cue ball should transfer to the colored ball. Just like that, right? That would be an example of a perfectly elastic collision. That happens in those little desk objects. You remember what those are called? Those little desk things that swing back and forth. Okay, they're called Newton's cradle, right? But yeah, they're a pendulum, right? A series of pendulums. You see that a lot. But we're going to deal with us having perfectly elastic collisions. Yeah. Yeah, that's right. Right. Everything.
If it's a big ball?
Yeah, good question. To have a perfectly conserved elastic collision like that, where everything is transferred, the objects have to have equal mass. Yeah. All right. And then inelastic collisions are when objects stick together. So they collide and then they stick and they move forward as one object. So in this instance, we don't have a conservation of kinetic energy because they're not sharing that energy. So any examples can you think of real life that are inelastic collisions?
Magnet on the fridge. You throw it at the mat. You throw the magnet on the fridge. Tape.
Yeah, sure. Okay, what else?
Car crashes.
Yeah. Two cars crash together and it's a mangled mess, right? What about if you tackle someone? Yeah, right? You're moving forward then as one object. Okay, those are all examples of inelastic collisions. If things collide and hook together, right? If you're trying to hook something together, we're going to see all of that in our lab, actually.
Do they have to be in motion? Like, you know those
No.
things that, like, you throw a ball and it's, like, Velcro and
Yep.
it sticks?
Yep.
So
That still would be an inelastic collision, right? One of the objects can be at rest, and then they'll move forward a little bit or whatever happens. Yeah. All right, so here's our equation for momentum. This is one that probably needs to go on your equation sheet. So here's our equation for momentum. Momentum is given with a P. Why do you think it has to use P?
Because not power. Power is P.
Okay, no, it is P, but it's a lowercase p.
But isn't power
Yeah.
lowercase p?
No, power is big P.
Momentum.
Why can't it use M?
Because mass.
Right, because mass, right? So they just have, it's another letter.
Because, wait. Little.
So momentum is mass times velocity. It's a vector quantity, which means it has to have what two things? Magnitude and direction. Magnitude and direction. So momentum has to be in the direction of the velocity since its velocity is a vector quantity as well. Okay, that seems really self-explanatory, and it should be. If I'm moving west, my momentum is to the west, right? If I'm moving east, my momentum is to the east. So the plus or minus that goes on the front of momentum tells us just direction, right? It doesn't tell us about the numerical value of it. It just tells us direction, okay? Units are kilogram times meters per second. That matches up exactly with what our mass should be measured in, right? Mass should be measured in kilograms. Velocity should be measured in meters per second. Right? That's where the unit comes from. There's no like super unit here like there would be with newtons or joules. It's just that, kilogram times meters per second. Okay, super unit's not a word, but derived unit. Okay, this is not on your slides, but I do want you to think about these two things. A large truck and a small car are moving at the same speed. Which is more difficult to slow down?
Truck.
The truck. How many of you think truck? How many of you think car? Okay, it's truck, right? The more momentum an object has,
Like a train.
yeah, that's right. It's way harder to get it stopped than something that's not moving as fast or not as much mass. Think about it the other way. Which one's easier to get started? Something that's light or something that's heavy? Right? It's easier to get started if it's light, right? The heavier an object is, you really got to put some force into it to get it started. It works the same way in the opposite direction. Okay? Because momentum is affected by mass and velocity. Okay? And none of those variables are squared, so they both kind of have equal weight there, right? In terms of what is dependent upon. Okay, so let's try this one here. A rolling boulder is found to have a momentum 4,015 kilogram meters per second east. If the velocity is 16.4 meters per second, what's the mass, right? It's literally as easy as it seems. Okay, momentum, or P, is equal to 4,015. The velocity is 16.4. That means I'm solving for my mass. So I'll go 4,015 equals mass times velocity. It is that easy, right? This isn't like a trick or anything. And it comes out to be, I don't know.
244.
Okay.
244. You don't have to. Oh yeah, you left.
244.8. And what would my units be?
Kilograms.
Good.
Does it get harder than that?
A little bit, but not a lot, actually. We use this MV equation a lot. Okay? All right, let's work through this question. What's the object's momentum after 1.2 seconds? Can we do something with velocity and our kinematics equations? What? We were given time, 1.2. It says it's dropped. So what does that tell me about my initial velocity? 0. Okay. I know my acceleration in the vertical direction is always negative 9.8. So can I solve for what my velocity is at that 1.2 second? Right? If I use my first kinematics equation, I think I can solve for the velocity at 2 seconds. VF equals VI, not 2 seconds, sorry, 1.2 times AT, right? That's one of the kinematics equations we'll have to use. All right, so final velocity at 1.2 seconds is equal to 0 plus negative 9.8 times 1.2. Tells me after 1.2 seconds, I'm moving at a speed of negative 11.76 meters per second. And so now I can solve for momentum.
So you say the speed of something falling does not matter about the weight of it, right?
Yeah, that's right. Right.
That's what we
The
were
velocity doesn't change, but the momentum does, depending on the mass.
And the direction would be south, wouldn't it?
I just kept it as negative, but yes, I mean it's falling, so yeah, it's moving in the negative direction. Yep. I wouldn't bother putting south because since it's in free fall, but as negative would be fine. Okay.
Well, it says
Okay. Because my velocity was negative, my momentum therefore has to be negative also.
So, say you dropped a penny.
Now let's look at how we build Newton's second law in with this, okay? So when we're looking at momentum changes, there has to be a force that's applied that changes that object, right? Things don't change direction without a force being applied to it. That's the whole point of inertia. An object in motion is going to stay in motion, or it's at rest, it's going to stay at rest, unless something else acts. Okay. Newton's second law originally, you don't have to write down this whole steps of equations, but I'm going to show you how we get there. Do you anyone remember what Newton's second law says? It starts with F net equals, mass times acceleration. That's Newton's second law. We already know this. Okay, but I'm going to walk us through how we can start applying this to momentum. Okay? Newton's second law says mass times acceleration. What's another equation for acceleration?
Something times 9.8.
Okay, that's his gravity. Mass times 9.8.
Change in velocity.
There we go.
Change in
Acceleration is the same as change in velocity over change in time. Okay? You don't have to write down all these steps if you don't want. I'm just going to get you to the final one. Now we look at this equation that says m times delta v over t. What does this equation look like? Something that we just learned, right? M times velocity looks like the thing we just learned, momentum, right? We didn't put the delta in there, but m times v is the same as change in momentum over time. So we can now apply a force, right? The net force of our system is also equal to the change in momentum over time. Okay, by adding the delta here, it doesn't change anything that we're doing. It's just saying we've got a change in velocity, okay? It still is mass times velocity over change in time. Just like when we have a delta t, it's not ever truly delta t because we very rarely have an initial time, right? We just have time. So this would be one that I would put on your equation sheet. F net equals change in momentum over time. Okay, I wouldn't put delta t necessarily, but change in momentum over time.
Do you want the mv over t also or no?
You can, but you also would know that, you know how to solve for momentum by just taking mass times velocity. So you could do it in 2 steps if you want. Okay. So let's try one like that. Okay. What force is required to stop a 488 kilogram wagon that moves at a velocity of 52 meters per second north in 2.3 seconds? So this is applying a force for 2.3 seconds to make this object come to a stop. Okay, it's moving north. We're applying a force over that time to get it to come to a stop. Okay, so that means I've got mass, I've got velocity, and I've got time. So if I'm looking for the force that needs to be applied, I'm going to take the mass times the change in velocity. So if I'm saying it's a change in velocity, what is delta V always equal to? Right, velocity final minus velocity initial. Right, so what's my final velocity in this case? Final would be 0. Initial would be 52 over time. 2.3, right? This one doesn't specifically come out and tell you that my final velocity is 0, but it tells me it comes to a stop. So we've got to take up that context clue. Okay? And so now when I solve for my force is going to come out negative. Does that seem reasonable?
It's moving in the opposite direction.
Yeah, that's right. I was moving north, so the force that has to be applied to stop me has to come from the south. So 488 times negative 52 over 2.3. I get a force of negative 11,033 newtons, or I could label it as 11,033 newtons south if I wanted to. Just not both. Okay. All right, 11,033 newtons from the south. Okay. Let's try this one. A 55 Newton object is traveling 36 meters per second. if the force required to bring the object to a stop is negative 42 newtons, how long did it take to come to a stop? Okay, so we've got a couple different things happening here. We've got a velocity, we've got a force. What is this value here? Is this the mass? No, it's not the mass, it's the weight. This is really the FG, right? Because it's measured in newtons. So it's not mass, it's weight. Okay, so we're going to have to use that in a little bit to solve for the mass. But what are we really solving for here? We're really looking for time. Time is going to be our question mark. Right, I've got to solve for time. So let's look at an equation that we can use here. I think we'll be able to use this. Force equals change in momentum over time. Right? But that means we're going to have the mass and the change in velocity in order to solve for the force it needs to come to a stop. Right? So if I know that the weight of my object is 55, how can I solve for the mass? Right? 55 newtons is equal to mass times 9.8 because we said this was FG. Okay, so 55. Am I moving too fast or are we doing okay? Are we hanging in there? Okay, that means the mass that I'm looking for here is going to be 5.6, yeah. So my mass is 5.61 kilograms. Now I'm going to come plug that into my equation here. Force equals mass times the change in velocity, right? It's coming to a stop. Oh, I'm sorry. They gave us a force. I didn't need to plug in an F there. They gave us a force of 42 newtons. 0 minus 36 over T. Any questions about how that equation got set up? Okay. Net force, or the force that took to change the momentum, was 42 newtons in the opposite direction. This is mass. This is change in velocity, and that's T. So what do I do when my T's on the bottom there? I can switch these two. Right? Algebraically, I'm just going to be able to switch them spots so that I end up with T equals 5.61 times negative 36 over negative 42. And I get a value for time of about 4.8 seconds. Agreed? Okay, what if my time would have come out negative? Time coming out negative is a big time red flag. Shouldn't happen. Okay? So incorporating out that time in there with this equation is not so bad. Okay. All right. Now we're going to look at something called impulse. Impulse is a fancy word for just saying the change in momentum. Right? I don't know why it gets its own separate name, but impulse is just the change in momentum. Okay? It is the same as delta P. Okay? Delta P is considered impulse. You see how this is the same equation just rearranged to solve for delta P? Right? The one we just learned was F equals delta P over T. All we did was rearrange. Right? Times T times T. Right? It's the same equation. Right? Remember with delta T, we've put it in there, but there's very rarely that we have an initial time that's not 0. Right? So it's still just T. All right. Equation applies to each object. When we talk about collisions, if we say, what's the impulse of an object that switches direction, right? Or that gets I don't know, a bat and a ball or whatever it is. The impulse will apply to both objects in the equation. Another way you can solve for impulse is the other version of momentum, mass times velocity. Okay. Mass times a change in velocity here. We put that in. And then what do we do if we have two equations that are set equal to the same thing? We can set them equal to each other. So if you want to put that on your equation sheet too, that's fine, right? We've got lots of variations of the same equations, one of them in set point and one of them in a delta like scheme, but they work the same. Okay, so delta just means we're dealing with a switch, right? If it doesn't have the delta, that means we're just looking at it in one moment in time. Okay, so tell me, do you feel okay about those equations? Right, delta P or that one. Any or all of those could go on your equation sheet. Whatever you want to do. Okay. So let's try one here. What force is needed to bring a 75 kilogram object traveling 44 meters per second north to a stop in 2.1 seconds? Okay. It's traveling north. So let's just think out loud before we do the math. My force should end up what direction? It's bringing that to a stop. So it's opposing my motion. So my force is going to have to come out negative. So just be thinking there. Okay, so force is my question mark. I'm given mass. I'm given time. And I'm given velocity. And is my velocity that I'm given right here, 44, is that my initial or my final? Initial, because my final velocity is 0, because it says it comes to a stop. Okay, so I think I could just use that where I set them equal to each other, right? I can say force times time, 2.1 equals mass times 0 minus 44.
Wait, can you tell me what the answers were?
Negative 1571.
Why can't you? I did that. I got the same answer, but I just used that. It's not the same equation.
Yeah, it is. F T equals
You're still
M
dividing it.
delta V. All I'm doing is dividing T. Right, it's the same.
You can use different equations.
It's just all the same setup. As long as it's got the variables in it, it's always going to work out the same. It's got the same variables. The equation's going to end up the same. Okay, so that is 75 times negative 44 divided by 2.1. I get negative 1,571.4 newtons. Okay, and the negative tells me my force was opposing that motion. So it could have been friction, it could have been a braking force, it could have been whatever, but it slowed it down. Okay? So just remember that impulse is a fancy word for change in momentum.
Will our equations always account?
All right, an object's dropped from a height of 8.4 meters. What's the momentum of the object after it has fallen 3 meters? Okay, it started at a height of 8.3 meters. It fell a distance or whatever of 3 meters. So now its height, oh, I said 8.3, it's 8.4, sorry. I don't know what I'm doing. Okay, 8.4 and 5.4. So we want to find out what's the momentum at this point, right? We need to know our momentum right here. Okay, it says it was dropped. So what is my initial velocity up here at the top? 0. So that means in order to find the momentum here, I need to know what's my final velocity at that point. All right, that's the very first thing I have to do. I've got to find my final velocity because I don't know time. I don't know force. I can't go about it solving it that way. So I've got to find my final velocity using kinematics first. Okay? So I know in kinematics I've got my displacements. So I've got to look at my kinematics equation and figure which one can I use to solve for final velocity without time.
Third one.
I think without time I'm going to have to use the third one.
Yeah.
Right? VF squared equals VI squared plus 2 times A times the change in, right? Or 3 meters.
Is it the
Right.
change in X or the change in
This would be change in Y because it's vertical,
Y?
right? So this would be change in Y. So 2 times 9.8 times 3. And then I'm going to take the square root of that. Something's not right. I'm missing a negative somewhere. Because I can't take the square root of... oh, here.
Negative.
Sorry, that should be negative 3. Thank you. So my final velocity comes out, it's going to have to be negative 7.67 meters per second. Right there I had to square root, so I had to add the negative back in. Okay, so my final velocity at that point, 7.67 negative. Now I can go solve for my momentum. Right, so P equals mass, 4.3 times the change in velocity, so negative 7.67 minus 0. And I get a momentum value of 33 kilogram meters per second. Right, 32.97. Okay, fine.